Next conversation is about reaction of alkene with a halogen. Typical halogens that we use are chlorine or bromine or iodine. Now, if you look at it, fluorine is never used in organic reactions of this simplicity. Even though fluorine is one of the halogens, it is not generally discussed, but it has enough drama. And not only that, it's small. It's very small. This reaction capitalizes on the size difference. If you look at the atomic size of fluorine, interestingly, fluorine is smaller than hydrogen atom. Okay, so size-wise, F2 looks like this. Cl2 is larger. Of course, there is an overlap. You have to have overlap, then only there is a molecule, right? Bromine is bigger. And of course, iodine is the largest in the bunch. What does that have to do with, what does size have to do with this reaction? Well, actually the success of this reaction is based on size. And you know one thing about intermolecular forces. These are diatomic molecules. So molecules are not polarized. These are non-polarized. However, because of the size, they have greater dispersion forces. Polarizability. Polarizability increases this way. What does the polarizability means? Its ability to deform the electron cloud. That means you can make temporary dipole. Ability to make a temporary dipole. If you look at it, a nucleus of both atoms is right in the center and the electrons are spread all over. And it's just the electron cloud. This cloud, when these two molecules kind of approach each other, what's going to happen is electrons start repelling each other. When they repel each other, you might be able to create a temporary dipole where electrons are all concentrated in one end and the nuclei are concentrated in the other end. Okay? And then next moment, this whole thing gets back and forth. Next second, it might look like this. The electrons are on this end and the nucleus is on this end. So the molecule kind of swaps between a delta minus and delta plus depending on the size. The larger the molecule, easier to deform the cloud, right? So increases the IMF. IMF stands for intermolecular forces. Right? Which makes, this is a gas, you know that, this is a gas, this is a liquid, and this is a solid. So this is F2, this is Cl2, this is Br2, this is I2. So size makes a difference in this case. So what are we talking now? We are talking about an alkene, which we have already discussed that it has the ability to function as a nucleophile. If it is a nucleophile, all it is going to be attracted to is electrophiles. Is there an electrophile in here? No. But if it is in this format, if it is a temporary dipole, if it is polarized, so when I have a bromine molecule in a polarized manner, if there is a temporary plus and temporary minus created, which is not which is not a permanent dipole. Keep that in mind. It's a temporary dipole. That instance where there is a delta plus on one of the bromines, electrons can be donated and it can be polarized this way. And interestingly, let me finish this reaction by overall reaction. When we have a CCl4 as a solvent, the product is, I will write the final product, one bromine here and exclusively second bromine in a trans location. Okay. Now, if we instead take bromine in water or alcohol, our outcome is going to be quite different. The product is going to be and here you're going to have OH, right? So this is a vicinal dibromo alkane, while this is a bromo hydrine. So it's not really, these are not same molecules. So adding molecule is same bromine, Br2, but based on a solvent, our outcome is different. And I think we have seen this before when we dealt with HBr. So let's look at the mechanism now. How do we write? How do we describe this? So let's say this is A and this is B. These are two different roads. So again, it's based on this polarizability. A smallest of these, which is very little, it's very difficult to polarize this. So the most common ones that we deal with are these three. And this is the easiest one to react with. Unfortunately, iodine is not very common in organic chemistry also because it's too expensive to handle. And most of the time iodine is, or halogens are used as something called leaving groups, which you don't understand at this point. We will talk about that at a later date. So let's look at the bromine reaction in case of CCl4. Right? Now, I'm going to go by this is the overall reaction. Now, if I'm writing a mechanism, what are the aspects we have to talk about? We have to look at the hybridizations, right? We have to look at regiochemistry, and if there is a regioselectivity. Is there a selectivity? Then we have to deal with stereochemistry and inspect if there is a selectivity or not. Okay, those are the aspects we are going to look at. So I'm going to take my three-dimensional view, or using a molecule that is lying down. So I'll write Me, right? And here I don't have anything, so I'm going to leave it as H, right? And you have a pi orbital or pi bond, and the electrons are here between these two atoms, right? This carbon and this carbon are making a pi bond. Now when bromine comes along, as we saw earlier, this can attack from top or from bottom. You understand that, right? So that phase or that phase, we can do that. But that aspect is going to complicate, or not complicate, it's just the added feature that we may have to consider. But for now, I'm going to look at the top attack, and you should be able to play the bottom attack just the same way. Okay? So I'm going to consider top attack only. Let's not look at that one when I'm writing a mechanism. So what does the transition state look like in CCl4? In CCl4, transition state looks like this. I have begun making space for a bromine. Which is connected to another bromine. Is that correct? So the pi bond hybridization of these two carbons is going to be compromised now, right? These electrons now are interacting with this bromine because this is a delta plus. Okay? Oh, it's going to point downwards. So you have a Me here, Me here. This is going to point downward, H, and both of them are going to be downward for that tiny instant. Now, had bromine come from the bottom side, they would have tipped upward. You understand that, right? Okay. So I'm looking from the top attack only. This is a transition state. All right. This transition state has to take a stance. Now you know it has two choices, and the two choices are bromine either marries this carbon or this bromine marries this carbon. In either case, this bromine is going to walk away. Is that correct? So the two choices we have are either the bromine is permanently married to this carbon or this carbon. So let's look at the two situations. Okay. So let's say the bromine attaches to this carbon. So I'm going to use a color now. I'm going to use the color. Okay. So you have a bromine attached here. Okay. So what is the other choice? Other choice is bromine attached here. I hope you understand that, right? Those are the choices. And if bromine attaches this way, these two are going to stay down anyway. Me, but this empty p orbital is going to be sp2, so these two are going to go back to their original state. They're not going to be tipping downward anymore. Okay. On the other hand, if bromine attaches here, these two will go down or stay down, while these two are going to go back to their original location, like this. Okay? There is a Me here, there is a Me here. And the p orbital is created with an emptiness. Okay? And what do? Having these two choices, as I said, is called regiochemistry. And with our infinite wisdom, we are going to say creation of a positive charge on this one, which is a primary, and creating positive charge on this one, which is tertiary. And we say tertiary is million times better than primary, so we are going to cross this out. That's a selection. So regioselectivity is taken care of. So I'm going to take this one now, right? This is going to react with the next step. Now, if I colorize them, if I say one bromine is this one, other bromine is this one, this shows that one of the bromine comes in step number 1, second bromine comes in step number 2. That's why I'm using two different colors. And we just abandoned this one from our conversation. Why did we abandon it? Because we already saw if this structure is C1 and this is my C2 structure, I just picked that C for the, because I use this as A, this as B, this as B, and this is C1 and C2, right? And in what context have we done that? We have looked at the energy diagram. And if the A is here, and B is the transition state, and C1 is going to be higher energy, but for C2 as the lower energy state, B is only that lower. So B changes shape. B is not a permanent structure because transition state is something that nobody is familiar with. It's only concocted based on where the intermediates are. If C2, which is a tertiary intermediate, C1, which is a primary intermediate, they are this is million times more stable than this one, 10 to the 6 times more stable than this one. That means this has to be abandoned. Why do you have to go through that big a hurdle while you can go through this hurdle? That's why I use this. Now what comes next is going to be here. Alright, so I'm going to take this molecule here and then we can talk about stereo selection. So is there a stereochemistry here? Is there a possibility of stereochemistry? Well, as long as that orbital has 2 faces, there is stereochemistry. Because second bromide, when it comes along, it can either come from the top side or a bottom side to attack. So that offers us 2 choices. So let's see. By having 2 choices is called stereochemistry. Making one of them is a selection. Alright? So what are the 2 choices? Let me rewrite that here. So I have C, and this is a ME, and I'm done with this side. This side I'm done because this side I already have a bromine attached. And keep one thing in mind, bromine has a lone pair. There is a lone pair here, lone pair here, lone pair here, right? And that is the reason I'm writing. Not only bromine has a lone pairs, it also large molecule, large unit, large atom, not molecule. So you have H, right? Now you have an empty p orbital, which is ready to do some business. At this point, the bromide that was kicked out, and we know the solvent is carbon tetrachloride, which is non-polar. Non-polar doesn't support any ionic material. So there is a positive charge on this one, this is miserable. There is negative charge on this one, this is miserable. So they have to marry with each other, however, right? So bromide has a choice of coming this way or coming this way. Now, there are some stories people make saying that when there is a size, when there is a electron cloud here and there is a electron deficiency here, sometimes, now this is just I would say imagination, because in chemistry all of it is generally imagination, because not everything is proven. So the people sometimes use this side is blocked by something called bromonium ion. They say bromine essentially sits like this. Now I'm not going to go and say there is a clear evidence to do this. I'm not going to say that, because it is not necessary for us to say bromine has actually made that triangular. And you know that making triangular structure is not really healthy in any molecule, because it is not going to be favorable. It's a 60-degree angle strain. So for that particular moment, if bromine is going to attack or create that triangular structure, now you have a slightly altered structure. Okay? Positive charge is now here. There are some arguments that say that this is what molecule looks like. I look at it as this is just a blocker. I don't have to show this. Sometimes in textbooks it is written as bromonium ion. Okay? I just want you to be familiar with the terminology, even though I have worry about saying that, because bromine doing that is not evidenced, at least to my knowledge, and for all argument's sake, it is not necessary to see that. I don't think there is a scientific evidence to prove that. Now, one thing for sure, there is a clear block here. That means this is never happening. It's never happening. Because of this size, so you have a steric issue, problem, and we also have electronic problem. What is the electronic problem? There is an electron cloud on bromine, there is an electron cloud on this bromide, this is bromide, there is an electron cloud on this bromine, so both of them are not going to be interacting well. There is that F equals negative Q1, Q2 or R squared problem. That means when you have two charged bodies coming next to each other, there will be repulsive force, right? We know that. That's the fundamental interaction in any chemical business, bond formation, otherwise. So this is having these two is a stereochemistry, crossing one of them is stereoselection. In this case, we make 100%. In previous examples, we had a hydrogen here. When there is a hydrogen, because it is tiny, if this is a hydrogen, let me see if I can show you the notes from the previous one. Right, this is one example. See, if this hydrogen was there, now this hydrogen doesn't have lone pairs, H2O can come this way or this way. Same way bromine could have come from either side. In one more example we did, we had bromine, this is the same thing, right? So essentially what we are looking at is, let me see, I don't find it. Right, I couldn't find it right away, but let me leave it at that. So we are going to have exclusive anti-facial attack. Anti-facial attack. What is anti-facial? This is syn-facial. Syn to this one, anti to this one. So the bromide has to come from this side. And it does, this argument is saying that if the one face is blocked, the second bromide, the bromide has to come from this side. Now interestingly, if this is a triangular one, what stops it from going there or there, right? So that's why I don't subscribe to this philosophy, because if it is triangle, both of these are just as good. That's why it is not easy to use this philosophy. In this case, I have this one permanently bonded, so I'm going to say 100% of the time it's going to do this. It's not going to do that. So due to stereo selection, that's a stereo selection. In our previous examples, we did not have stereo selection. That's why we got 50-50 or racemization. Here there is no racemization. So what do we get then? We get the product that looks like this. The product is, right? Product has, the first bromine is here. Nothing happens to that one, right? The second bromine atom, bromide, is going to attack here, right? That makes the molecular geometry look this way. Whoa, that's a H. That's a H. And then your two methyl groups are going to tilt upward. These have to tilt upward to make space for this, right? Because this is an sp2 carbon, now it's sp3 carbon. There's one methyl, the second methyl. Okay? So this is the product we are going to get exclusively. Okay? Let me take a different example. What would happen if I take a cyclohexene with the methyl substitution on it? Now if I react with the Br2 in CCl4, I should be getting 100% of the time a Br If Br is that one, the other one has to be N tied to it, and this is how we show it. Okay? But is it possible that this bromine is facing me? In that case, that bromine is going to be facing underneath, under the paper, right? Above the paper, below the paper. Now, what is the relationship between these two? The relationship between these two is enantiomeric relationship, because you are going to have exact opposite. But there are two chiral centers. Both of them are flipped. Remember that. If this is R, this is S. This is R, this is S. Okay? Now, how am I going to draw? How am I going to draw this one in a plane? So here is how I will show. So let's say I make this cyclohexane ring planar, and the double bond was here. Let's say double bond was here, and then there is a methyl group here. Double bond means you have a pi bond here, right? Imagine the three-dimensional view. Now, when the bromine comes along, again, I'm going to use colors. When I use colors, it gives us an ability to create a sequence. Okay? Where would the first bromine go? The attack is going to be like this or like this, right? Attack is going to be like this or this, right? So I'm going to write everything that is going to happen now. That means we will do, this is my A, this is my B, right? If I did A, this is what's going to happen. So if A happens, A has two choices. Why A has two choices? A has Br attacking here or here, and similarly B has Br attacking here or here. So this is my A choice. The B choice is going to be, you have to start visualizing these rings. Now remember, I should be using chair or boat notation, right? There is no such thing as a planarity. This ring is not planar, you understand? But just for illustration purpose, I'm using the plane. Now there is a lot of fallacy in my drawing, a lot of mistakes, because I should not be drawing this as a planar structure anyway. Right? So I'm keeping the methyl group where it is. Okay? So let's say my first, the A choice is going to give you a either attack bromine here, giving a positive charge here, right? Or attack Br on this one, both of them are top, and empty p orbital on this one. In that case, positive charge will be on this one. And we know there is a wink wink. We are not going to pick this one as a choice because this is a secondary carbocation, this is a tertiary carbocation, right? That's why we use that methyl was the place there. So we are going to say this is not going to be happening. This is going to be not going to happen. Let's go for the choice B. Choice B also has a Br can attack here and create a positive charge here, or Br attack here and create a positive charge there. Now in that case, that methyl group has to tip upward. It's not going to be pointing that way. Remember that. So I'm gonna flip that methyl group there, because you got to create a three-dimensional illusion. Let me see if I can do a quick creation there, because I don't want it to be factually wrong. So I do have to erase this. Okay. All right. Now that's a methyl. Which one are we going to abandon? We're going to abandon this one, because this is a secondary carbocation, this is a tertiary carbocation. So this is where we made a regio selection. So this is my B choice. And we selected this one to be thrown out, just like this one is thrown out to be deleted. Now the next step is bromide addition. Next step is second bromide. Now has a choice of attacking from this side or from this side. And if we attacked from this side, it's synfacial. If it is attacked from this side, antifacial. I'm going to cancel that, because having bromine here, this bromine is going to obstruct. It's not going to allow this second bromide come this way. Same way, in this case, second bromide had a choice of coming from top or from bottom. In this case, this bromide is sitting on the bottom side. So this is going to be blocked. So this is the only one, 100%. Right? So understand that we have a clearer answer in this case. So this is going to be cancelled. This is going to be 100%. So this leads to a single product. This leads to a single product now. So what do we get? We get this same thing. By the way, this answer is repeated here. Okay, I'm just showing in a three-dimensional view. So what happened here? You have a bromide is not going to go this way. It's going to come this way. That means this methyl group has to flip upward. Aha! This methyl has to go upward. Right? This methyl has to flip upward because it is a planar molecule. This has to flip upward. And in that case, bromide is going to be here. Okay? The first bromine was right here. That I can't do anything about. Okay? This is methyl. And what's the product in this case? Right? Now, in this case, bromide is not going to come this way. It's going to come from top side. So, the methyl is going to go further down. Further down. And then second bromide is attacking here. And the first bromide has come from here. Now, this is why I said, look at that. If this bromide was on this side, second bromide has to be opposite. That doesn't mean that this is always on the top, but wherever they are opposite of each other. And that's what I'm showing here. Understand? And now if you look at it, these are enantiomers. These are enantiomers. Because there's a chiral center here, there's a chiral center here. There are two chiral centers here. In this case, there are two chiral centers. Is there a possibility of mesomerization? For a mesomerization, both of these chiral centers have to have same attachment. In this case, there is a methyl group. In this case, there is a hydrogen. So this cannot be mesomer. These cannot be mesomers. Remember that. Right? And they cannot be considered diastereomers either, because they are exactly opposite of each other. Right? This is down, that's up. This is up, this is down. So this is the beauty of reaction in CCl4. All right. Now we have not yet considered hydride shift and methide shifts. Right? Let me consider that as an example. Now let's look at this. Let's look at this example. Right? So suppose there is a double bond here, but there is a methyl group here. Okay. Suppose there is a double bond here, there is a methyl group here. What might happen? But you know what? Before that, let me take a slightly different example. Let me not include that. Okay? Let me not include that. Let me just keep that much, because that example will complicate it a little bit. Now if I use Cl2 in CCl4, let's say, again, that's a solvent, that's the reactant, right? What will happen? Step number one. Now remember, if you do write this as an answer, if you followed the lead that you took here and you simply wrote that, that'll be considered a wrong answer. This will be a wrong answer. Do you know why? Do you know why this is a wrong answer? Because you are going to create a carbocation rearrangement in this case. So in step number one, remember we discussed this. We looked at any time there is a carbocation, we have to think about rearrangement. So what do we do in this case? Right? So when we do this, our step number one, I'm going to skip all the regiochemistry, stereochemistry and all that aspect. I'm not going to bring it or talk about it. We'll just deal with it. Okay? So, and you know that I've already made the regio selection, placed a positive charge there. I've done the regio selection already. I didn't show the transition state. I already did the step that led to a choiciest, because you know that if I attach chlorine here, put a positive charge there, that's not acceptable. So why play drama? Now here comes the issue. When there is a carbocation, secondary carbocation, is drooling over the next atom, there is a possibility of making tertiary. In that case, the hydride shift, H- shift, will lead it to this carbocation. Right? So let's say I have chlorine attached here. Now that this hydride, and let me use a color just for the sake of, this hydride is now here. Okay, that means carbocation is on this location. Okay, at this point, chloride, the chloride, incoming chloride, doesn't get bothered by this chloride because this is far away now. So there is no stereo constraint anymore. So at this point, I'll simply show it this way because it don't really matter. It just doesn't matter because it's not related to this one anymore. It's not affected by this one. So the product is, as I said, this is the wrong answer. This is an obvious multiple choice flaw. Keep that in mind. This answer will be there in a multiple choice. And that's a trap answer. So what's going to happen is your answer is going to be this one. If I had a first chlorine is this one. The second chlorine is this one. Now first and second chlorine is for our conversation only, because we don't really have a label. We don't really have a label on the molecule when we get the final product. You see how different this is? This is the answer. This is the correct answer. This is the correct answer. This will be the correct answer, not that one. In that case, I don't have to show wedges and dashes. Let me take one more example before I leave this. Actually, two more examples, right? So let's take one more. What is going to happen? This is what we are trying to accumulate our information now. We are trying to accumulate information. What would happen if I have that? Now if I use bromine in CCl4, in this case, I am going to get, anyone thought about it? One bromine is going to be here. The second bromine is going to be attacking here, obviously, but then there is a methyl shift is going to happen. There is a methyl group here. Remember, these are two methyl groups. Okay, and keep that methyl. Right? But one of the methyl has shifted there. You see, this is going through methyl shift or methide shift. involved carbocation rearrangement. Well, obviously you know now my next example. What is my next example? Anyone? Anyone? Anyone can imagine what is my next example? My next example is what is going to happen if I have that what is going to happen, and I'm making a mess there, let me clean it up. What is going to happen if I have a ring and it's a restricted ring? It's a restricted ring. What do you mean by restricted ring? This ring is in trouble. Why is it in trouble? It's a cyclobutane ring. Cyclobutane ring has a ring strain, and every opportunity it is going to expand again. Let's see the obvious answer here. Wrong answer, obvious wrong answer. What is the wrong answer for this one? That will be there on a test. This is the obvious wrong answer. And it may not sound like a bad answer because that's what we saw in every case. Bromine adds to one carbon, other bromine adds to other carbon. But it's a wrong answer because we are talking about rearrangement possibility. This is the correct answer. So in this case, what is the obvious wrong answer? I'm not going to write it. You can write it. One bromine here, one bromine here, right? So let's say this is a Cl2, CCl4. By the way, I don't have to write CCl4. I can write hexane. Hexane. I want you to be familiar with these solvents. Hexane. What do you know about hexane? Hexane is nonpolar. Nonpolar solvent. That's all that matters. It's not water. Is hexane water? No. Hexane is nonpolar. That's all that matters. That means CCl4, hexane, toluene, benzene, dichloromethane. I can give any solvent. The drama is going to be still the same. Now what's going to happen? Step number 1. I will have that carbocation created, right? And if we don't look closely, you will see there is a possibility of a method shift. That means I can move those electrons like A to this carbon. Just like I moved that methyl group. See, why did we get this? Why did we get this? Why did we get this? We essentially had a method shift. Me. What was the intermediate? We had a Br here, positive charge was here, which was secondary. When there is a secondary, if I simply move that method on this one, I can make a tertiary. Is it an expensive process? Yes, it is quite expensive, but the reward is great because you are going from secondary to tertiary. That reward is overcome. So no pain, no gain, right? So essentially we have one of the methyl group shifted to this one. In return, positive charge happened to be created on that carbon. So this was secondary, now it is tertiary. In terms of energy diagram, we have seen this before. We have gone from a situation, let's say I started molecule A, right? And I went through possibilities of, if you remember my previous terminologies, a B and C1, right? But I used a C2. C2 was my choice, and we abandoned that, regio selection. The C2 was this one. C2 turned into C3, which is this one. Why C3? let me make it D, because it's a totally different charge, different molecule. It's a D. That's a D. I'm not going to make it C3. That's a D now. D is what? This is secondary, this is tertiary. Right? Now it is more favorable. That's how much? 10 to the 3 times. So you can say D is, so tertiary is 10 to the 3 times more stable than secondary. We know that. So going from there to there, is it only that much? No, we have a cost. There is a high cost to go there. High cost. What is the high cost? Because we got to break a sigma bond. There is a sigma bond to be broken. We know that. But reward is there. And then last step is bromide attacking, and that's how you are going to get this other product, right? So I didn't show the energy diagram, but that's what the final product is. D, this is E, let's say. That's E. Okay? Right? This is B, this is C2, C1, this is B. Now you don't know what B was, so we just imagine now, right? D is definitely understood and E is definitely our product. Okay? So there is a outcome base. This has a different drama. It's the same thing except this is a method shift. Method shift is a ring expansion. Now if you look at it, what would happen is you create a 5-membered ring. So now we have a 5-membered ring created. So this will give you, this is where we have to start numbering carbons. 1, 2, 3, 4, 5, 6, let's say 7. This is my 1, 2, 3, 4, 5, 6, 7. What is going to happen is a 2,6 bond is created. A 2,6 bond, when it is created, a 2 connected to 1 connected to Cl, that is going to stay there. This is 2, this is 6, right? 6, 3, the bond between 6 and 3 is gone. There was a 6-3 bond. It's no longer there. But 6 is still connected to 5. 5 is still connected to 4. 4 is still connected to 3. 3 is connected to 7. Right? Do you notice that? So 2,6 bond is made, but 3,6 bond is gone. Who got the positive charge now? 2 used to have a positive charge. 2 had the positive charge. Who now got the positive charge? Look at the electron count. These electrons belong to 3 and 6. These 2 electrons were property of 3 and 6. 6 is still holding that electron. 6 did not lose. Who lost it? 3 lost it. So the positive charge is on this 3. Positive charge is on 3. Okay? Now, what is the reason? What is the driving force for this? You went from secondary to tertiary. This was a secondary carbocation. This is a tertiary carbocation. So that's one advantage. On top of that, ring strain from 4-membered ring to 5-membered ring is created. Ring strain is enormously reduced. Right? Now we are going to have a final attack. The final attack now is going to be second chloride is going to come and attack this carbon. Right? Carbon number 3. So the final answer is going to look like this. Okay? What is the obvious answer? What is the obvious wrong answer? Obvious wrong answer is this. That's the wrong answer. That's the right answer. So here 1, 2, 3, 4, 5, 6, 7, while this is 1, 2, whoa, I made a mistake. That was a mistake. That's definitely not the answer. I think one of you or some of you already caught that. Numbering is where you are going to catch your mistakes. That's why never rely on memorization. So chlorine is on 3. Chlorine goes to 3 carbon. That's a 7. This is 5. This is 4. Right? Look at the numbering. I'm keeping numbering same. So this is what we have to be focusing on. How do we do the carbocation rearrangement? So this is not really a simple story. I already told you that introducing carbocation rearrangement, life would have been easier if we didn't have to include that. But this is not our choice. This is not my choice. Reactions are going to do what they want to do. They don't listen to me. This is not something that I can control. This is not my purview. So it is, when we are learning, it is necessary for us to assess all aspects of it, right? And if I don't mention this and spring this up on either next exam or final exam, you are not going to be happy. So that's why I have to introduce these aspects, okay? Since we have learned already, this is the wrong answer. Remember that. That to that is the wrong answer because it's easy to see. Now, here is one last example I'm going to take and we'll move on. If you think about a I think this, after studying this, after looking at this one, this example is not going to be that difficult. This example is not going to be that difficult, okay? If I have a double bond here and I have this, okay? Oh, let me make it a little bit more, I won't say challenging, more interesting. Let's say Br2 in CCl4, and what would happen if I have that, or what would happen if I have that, okay? Same reagent, what would we get, okay? What is the product? Same reagent, in each case, let's write the product. In this case, bromine has a choice of attacking here or here in first place. Which one is better? That's a secondary, that's a secondary. Both of them are just as good, right? So the first instance, first glance, you are going to say, the intermediate formed could be 50% of the time adding bromine here, right? Positive charge there, and the 50% of the time bromine here, because we didn't have a choice, right? Now this one is stuck. This is stuck. This is obviously stuck, right? So next step is going to be bromide addition is going to be this. This is why the answer is going to get a little bit complicated. That would be an answer if this is the case. The 50% of the time you are going to get this. But if it is this one, if this is this one, then there will be method shift, and after method shift, I'm going to show method shift. I'm not going to write this. What's the product then? The product is going to be method here. First bromide is here, second bromide is here. This is something we have seen earlier, right? So we will get two products now. One of them is this, because this is 50-50. 50-50. Okay? So if you wrote this, I have to give you credit. If you wrote this, I have to give you credit. Because since there are two possibilities. Okay? Now which of them is the predominant product? Now the fact that this is able to go through tertiary carbocation, these were secondary, but this started out as secondary, turned into tertiary. So this will turn out to be major. This will be minor. This will be major product because there was a tertiary carbocation involved. This is only secondary carbocation in this case. While this is secondary, remember this is secondary, but it's going to turn into tertiary. How does it turn into tertiary? It turns into tertiary this way. Because we did the hydride methyl shift. You did the methide shift to move that methide group there. So that methyl group is gone there. So the positive charge is here. That's why you ended up adding bromine here. So that finishes the story for this example. So this is major, this is minor. What's going to happen in this case? Well, there is a 50% chance it's going to give attack here, 50% times it's going to attack there. So in that case, now we have a little bit interesting scenario. Okay? So what's going to happen? If first one attacks here, if the bromine attacks here, first one, makes a positive charge there, right? Or bromine attacks here and positive charge here. Both of these cases, we have a possibility of hydride shift. Hydride is going to shift there. Remember, we could not do hydride because there was no hydride here. There was a methide shift. There is no hydrogen here to shift. That's why it's a methide shift. So this hydride goes there, or in this case, this hydride goes there. Correct? What will that give you? This will give you positive charge on this one, and eventually the product is going to be this. First bromine is here, that methyl group is right there, we didn't do anything to it, but the second bromine went there. Second bromine went there. Look at the difference. You don't add bromine, not going to work. In this case, bromine is not going to work. What about in this case? Well, after the hydride is shifted there, positive charge is going to be on that carbon. So my final answer is going to be is that correct? And they are the same. They are same as long as I didn't make any differentiation. So in this case, in this particular example, there is only one answer. You can either draw this one or this one. They are same. What does it happen in this case? In this case, is there a possibility of rearrangement? No, because if I make a positive charge here, that's secondary. If I make a positive charge here, that's a secondary, and there is no place to rearrange, so they'll be stuck there. So you'll have 50-50 two products. What are the two products? In one case, I'm going to add one bromine here and positive charge here, which will give you second bromine has to attack trans. Is that correct? Same way, in this case, let's say my first bromine attacked this way. The second bromine has to attack trans to that one. So that should give me this as the answer. Now, by taking these many examples, you should understand the drama of bromination in case of CCl4. Now turned out to be the same molecule, sorry, they're not same. They're enantiomers of each other, 50-50. These are enantiomers of each other, okay? So in this case, you are going to get a mixture. So again, as I mentioned to you, getting a mixture is not really a goal in organic chemistry. But isn't it necessary for us to learn when there is a mixture available so that we can avoid them in a synthetic process? All right? So this is a reaction where we finished that part. We finished this much. Vicinal dibromide story. But do we always get vicinal dibromide? No, because we saw that there is a possibility of carbocation rearrangement. Vicinal means adjacent carbons. Do we get bromines added to adjacent carbons? No, we don't. We don't always get that. We saw there is a possibility. Our next lesson is going to be on this one. Okay? Our next lesson is going to be in this one. I'm going to stop right here and we'll start next.